presents a co-clustering model to perform a fair recommendation. And well, as I said, as you said previously, it's a joint work with Jean-Benoît Léger and Yves Grandvalet from the Université de Technologie de Compiègne in France. So a few introductory concepts. That is, first, the collaborative filtering. That is a method that aims at building a recommender system by using some feedbacks that users give to some items. And the goal is for missing feedback is to get the value of that feedback, and in order to recommend or not recommend that items to the users. So all these collected data on the left could be recognized by using a matrix where the rows are the users and the columns are the items, and the entries of this matrix are the feedbacks of the users. And the goal is to fill the missing value of this matrix. So many methods exist to perform this goal, and one of them is to use a co-clustering model. So the idea behind using a co-clustering model is to help to identify some group of users having some similar preferences for some similar items. And one example of a co-clustering would be the following on this matrix. That would be able to reorder the rows and the column of the matrix to reveal two partitions in the matrix. The first partition on the rows, here with three groups on the users, and a second partition on the column of the matrix with here two groups of items. And by doing this, we would be able to summarize this clustering and say that, for example, that users that would belong to the red group here would give a black ratings, for example, with a given probability to any items that would belong to this green cluster. So, but the problem is, what if the summary of the co-clustering is the following, where we have two groups of users. The first group would be mainly composed of females who would love some romance movies and dislike some war movies. And on the opposite groups, we would have only males that would have some opposite tastes on these same movies. We could wonder if it is a desirable situation, and in fact, if it is fair, if it is a fair recommender system according to sensitive attributes that is here the gender of the users. So what we propose here is first a model of collaborative filtering that is able to model some ordinal user responses, typically some ratings ranging from 1 to 5. And as I said, this model is based on the co-clustering model and will uphold a parity to ensure some fair recommendations. So I gave the first definition, that is the epsilon parity. The formal definition is on the right, but if you just look at the example on the left, what we call the epsilon parities is that we have in each group of users roughly the same proportion of females or males, whatever. And if there is a difference between these proportions, it is what we call the value epsilon. So it means that the smaller the epsilon is, the better will be the parity of the clustering. So the model we proposed is the following. It is based on already existing model called the Latin block model that supposes that users and items belong to groups, and that the ratings that we consider as continuous for the moment are all independent and Gaussian distributed with parameters here, μQL, that depends, in fact, in the membership of the users, in the group membership of the users and the group membership of the items. So we're going to use this model and we're going to complexify it. First, by adding two Gaussian variables, I and bg, that model some individual effects of the user I and some individual effects of the object G. And these individual effects are added in the Gaussian distributions. So as I said previously, we want our clustering of users to respect the definition of parity I gave. So to respect this parity, we are going to model the interaction that will exist between the sensitive attribute of the users that we denote by SI and the object G. And by doing this, by modeling the couple SI CGI, we hope and we expect that the clustering of users to be independent from this sensitive attribute SI. So until now, the ratings were continuous, but what we observe in the matrix is either some missing values or some discrete ratings. So we are going to discretize the Gaussian space with some fixed thresholds, and we can say that the ratings will have the value 2, for example, if the continuous ratings is between these two fixed thresholds. And finally, we need the missingness model, and we simply assume that all the ratings are all independent. The probability of observing ratings are all independent and follow the same probability P. So to infer the parameters of our model, we use some classical log likelihood maximization. However, the log likelihood is not tractable, so we are going to use some variational inference that consists of optimizing the lower bound of this log likelihood. And we simply update all the parameters of our model by using some classical stochastic descent algorithm. So once we have all the parameters of our model, we can define a relevant score of item G for user I, and say that this relevant score is composed of the co-clustering effect plus the individual effects of the user and the items. But very importantly, here we are not going to use the couple SI CGI. I remind you that model the interaction between the sensitive attribute SI and the object G. And by using this relevant score, we are able to compare two items and say that item G is preferred to item G prime if RIG is above RIG prime. And we come to this definition of what we call epsilon fair recommendation. And we say that the recommended system is said to be epsilon fair with respect to a sensitive attribute S. If for any two items G and G prime, we have this following quantity. That is that the proportion, for example, of females that would prefer the object G to the object G prime is roughly the same that the proportion of male that also prefers the object G to the object G prime. And if there is a difference of proportion, we denote this difference of proportion by epsilon. So the smaller the epsilon is, the fairer would be the recommendation. And we have this following property that says that if the clustering of the users respects the definition of the epsilon parity I gave previously, then the recommended system that relies on this relevant score here would respect naturally this epsilon fair recommendation definition. So we made a few experiments by using the Mobilence 1 million datasets. That is a dataset that gathers ratings given by users to movies, ranging from 1 to 5. And what is interesting with this dataset is that we have the gender of the user, and we're going to use the gender as the protected attributes for the co-clustering model. So the first question we can ask ourselves is, what about the gender parity? Is it respected or not respected by using our model? So we computed the K2 statistics for several baselines. And the results that you can see here by using our model called the parity LBM is that our model is consistent, if you look at the p-value, with the clustering parity hypothesis. Whereas if you are using some other baselines of co-clustering models that ignore these sensitive attributes in the clustering, the parity is not obviously respected. The second question we can ask is, what about the fairness? So to do this, we computed the value epsilon of the epsilon fairness definition I gave. And if you look at our model, it improved the value of the epsilon fairness compared to the standard Lattenberg model. That is exactly the same model as ours, but that ignore the sensitive attributes. And what is also interesting is that if you're looking some other baselines, classical baselines such as SVD, you can see that matrix factorization is in fact quite unfair. First, third question is what about the recommendation performances? So to do this, we computed the normalized cumulative gain, which is a ranking matrix. And if you're looking at the light blue, you can see that between our model, the parity NBM, and the standard atom block model, there is some kind of loss of performance, but it doesn't appear to be significant. And unfortunately, if you still look at all the co-clustering models in light blue, the co-clustering models perform worse than the standard matrix factorization, but in fact it is quite low. And finally, if you look at the dark blue and the green, you can see that all the models still have some disparate performances between the males and the females. But having equal performances between sensitive attributes is relative to another definition of fairness that we were not aiming at the beginning. But we can still be interesting to try to reduce these disparate performances by modifying the criteria of pertinency according to an item and a user I. So here the co-clustering effect plus the individual effects, but if we add this effect, the lambda CG, it would mean that we will try to inject some stereotype in the recommendations. But what is important here is that we inject this stereotype for all the users, meaning that we're going to keep the value epsilon of the epsilon fairness we gave. But by modifying the value epsilon, by modifying the value lambda of this score, we can try to reduce the disparate performances up to a point where we have equal performances between males and females. So to conclude, very general conclusion is first that ignoring a protected attributes is not a good idea for fairness. And we should rather consider the protected attributes directly in the modeling process or via constraints inside the model. But it's also possible to do this via post or pre-treatment on the data. So if you have any questions, you can ask me.